Today we'll be looking at the synopsis of the chapter current electricity. Uh, what current means is that the definition of current is nothing but flow of electrons. In any normal conductor at a given temperature, without having any potential difference, electrons flow in various directions. So, due to which, across any section, if you take the section of this, across any section, the number of average electrons which are flowing is 0. Since this electron flowing here is cancelled by this electron flowing here. So, on an average, there are 0 electrons which are flowing in a given specific direction. Whereas, when a potential difference is applied across these two terminals, all the electrons being negatively charged start flowing towards the positively charged terminal, and thus an electric current is set up. In a conductor, when the potential of positive and negative is applied, electrons flow from the negative to the positive terminal. However, for ease of conventions, the direction of current is assumed to be in that of the opposite direction, as positive to negative, as it can be assumed that anything that flows from a higher potential to a lower potential. Hence, positive terminal is taken as higher potential and negative terminal is taken as lower potential. And hence, the direction of current is assumed from positive to negative, even though the flow of electrons is actually from the negative terminal to the positive terminal. Once this base is established, we will look at Kirchhoff's law. So in the year 1842, Gustav Robert Kirchhoff, he stated two laws regarding to current. So Kirchhoff stated two laws. The first law is known as junction law, or it is also called current law. This law states that at any point in a circuit, say there is an electric circuit, just a point which is in an electric circuit, I1, I2 and I3. So at any point in an electrical circuit, the algebraic sum of all the currents at this point is nothing but 0. This law is in accordance with the law of conservation of charge. So this law can be stated as I1 plus I3 is equal to or minus I2 is equal to 0. Note here the sign conventions which are used. The currents which flow towards the junction are taken as positive. In this case, I1 and I3 flowing towards the junction, whereas I2 is flowing away from the junction, and hence it is taken as negative. The second law of Kirchhoff is known as voltage law. Or also known as loop theorem. What this law states that in a closed loop, the summation of potential differences between the various elements is nothing but 0. For example, in this closed loop, the sum of the potential difference across this resistor is nothing but IR, and the potential difference or the EMF across this battery is E, is equal to 0. So when there are multiple number of resistors and batteries or other components such as capacitors and inductors, so this law, summation of IR plus summation of E is equal to 0, is valid. There are few sign conventions in this too. So the sign conventions which are used in this are, when in a loop, when trying to figure out the sign of the potential difference across a resistor, for a resistor or other passive components, if the direction of current is same as the tracing direction, it is considered as negative. Whereas for sources of potential such as batteries and other EMF sources, if the direction of flow of current through them is same as the tracing direction, it is considered as positive. To illustrate this with an example, this is a simple loop. This is a simple loop with current I, a source of EMF E, and a resistance R. So the current flowing through this direction is in this anti-clockwise direction. We need to start tracing from any specific point, either a source of potential or a resistance. In this case, if we start from the point E, what we need to keep in mind while tracing the direction and trying to figure out the sign conventions is, an easy way to remember is, look at the potential, whether the potential across that element increases or decreases as we go about that point. Say we start from this point, and if we want to trace it in an anti-clockwise direction as the current is flowing, from over the over the cell, the potential would, this plate is at a higher potential, whereas this point is at a lower potential. So if we are tracing it in the anti-clockwise direction, the potential is increasing, hence plus E, and at this point the potential is greater and here it is lower, since the current is flowing in this direction. Hence, across this resistance, the potential can be written as minus Ri equal to 0. This second law, also a voltage law, is in accordance with law of conservation of energy. Next we will see Wheatstone's network. In 1843, Charles Wheatstone invented a method in order to find out an unknown resistance. This includes a construction of three known resistances which are placed in the arms of a parallelogram or a quadrilateral, and the center arm has a galvanometer in it. This arrangement is connected by a potential difference, and a key is provided to turn on and off the circuit. So the principle is that when this is known as a Wheatstone's bridge, there are four resistors connected in four arms of the parallelogram, and the opposite ends are connected to a galvanometer. These have resistance R1, R2, R3 and R4. So the principle is that when the bridge is balanced, no current flows across the galvanometer. Hence, galvanometer current is equal to 0. When is this condition achieved? This condition is achieved when the value of resistance is R1 and R2 is proportionately equal to R3 and R4. The relation is such that R1 upon R2 is equal to R3 upon R4. This is known as condition of balance. From this Wheatstone's network bridge, a popular method known as meter bridge this is basically the principle, and this is the governing formula. Based on this principle and this governing formula, a method known as meter bridge is developed for practically finding out the unknown resistance X using a known resistance R and a wire of 1 meter length or 100 centimeters is used, and this is connected to a potential, a key and a rheostat. The purpose of the rheostat is in order to vary the potential gradient. The use of rheostat does not actually affect measurements in the potential in the meter bridge. Between the unknown resistance and the known resistance, a galvanometer is placed, and this galvanometer can slide across this 100 centimeter wire with a device known as jockey. Jockey is nothing but a instrument or a device which is pointed metallic device which can be used to place at any which can be used to maintain contact at any point on the wire. How the unknown resistance is measured is that after placing an unknown resistance, the current is allowed to flow through the circuit and the galvanometer is touched at various points. This resistance R value is selected suitably, and it is preferred that the galvanometer should show zero deflection in the middle 1/3 of the wire. That is selected for better accuracy of the results. So once the current starts flowing, the jockey is touched at various points on the wire, and the point at which the jockey shows null deflection or the galvanometer shows null deflection is taken as the reference point. Say it is at a length of L. Since the wire is of uniform length, the potential gradient or the rate of change of potential per unit length of the wire is constant, and hence the resistance in the wire at any point is directly proportional to the length of the wire. So since the resistance at any point is proportional to the length of the wire, as we seen on the previous case, when the jockey is touched at point L, there is zero deflection in the galvanometer, and hence the relation as H upon R is equal to the length L divided by the remaining length, which is nothing but 100 minus L. From this relation, the value of unknown H can be found out. This relation is useful to find out value of unknown resistances, like when we know the value of standard resistances R, which can be selected from the resistance box. After looking at Wheatstone's meter bridge for finding out the resistance of finding out the value of unknown resistance, there is something known as Kelvin's method, which is used to find out the resistance of the galvanometer. In this method, instead of placing an unknown resistance across, in place of that, a galvanometer is placed, for which we need to find out the unknown resistance. This is a known resistance R. The same meter bridge is used, 100 centimeters, and it is connected with the source of potential and a key. The difference in Kelvin's method is that there is no galvanometer placed on the jockey arm, as it was in the Wheatstone's meter bridge. There is no galvanometer. The only galvanometer is placed as an unknown resistance, and this galvanometer itself is used to find out the zero deflection point. In Wheatstone's meter bridge, zero deflection method was used. That is, when no current flows through the galvanometer, when the bridge is balanced, there is no current flowing through the galvanometer, and hence zero deflection used to be used. But whereas in Kelvin's method, since current is always flowing through this galvanometer, null deflection method is used. Null deflection method is used, in which when you look at the galvanometer reading, we try to achieve a specific value initially. Like when the circuit is closed and current is flowed, the galvanometer will show certain reading, and we take that as a reference. And in order to measure the resistance, what we do is we touch the jockey at points A and B, that is the extreme ends of the meter bridge. And we should take a note that the readings are in the opposite direction, and the center point is taken as the reference. Using this concept, we find out the specific point on the meter bridge where even without touching the wire and touching the jockey, the galvanometer shows the same deflection, hence the term null deflection. The bridge is said to be balanced, and the condition of balance, that is G is equal to R times L upon 100 minus L. This relation is again used in order to find the unknown resistance of the galvanometer. Let's look at potentiometer. Potentiometer is an instrument which is used to measure the EMF of various components. A voltmeter measures the potential difference. But a potentiometer measures the EMF across the cell, which includes the internal resistance too. So the principle of potentiometer is that a long stretched wire, generally varying from 2 meters to 10 meters, is connected via a rheostat. The purpose of this rheostat again is just to change the potential gradient, and hence there will be a small resistance of the rheostat as well. Since potentiometer measures the EMF across the cell, all the possible resistances would be taken into account. The small internal resistance R of the cell, as well as the R, which is the total resistance of the wire, will also be taken into account. When the circuit is closed, the current flows through the potentiometer wire, which is equal to voltage across AB upon the length of the wire. Since the wire is of uniform length, the potential gradient V is at any point, say at point P. So VAP upon L is constant, and this is known as the potential gradient. So the total current which is flowing through the entire circuit, considering the internal resistance of the cell as well as the small resistance that the rheostat provides, is nothing but I is equal to the total EMF, and which is the term which we generally need to find out, divided by R, the resistance of the potentiometer wire, plus small internal resistance of the cell and the resistance of the rheostat. The potential gradient of the wire is given by, since here, so the same as this, VAP upon L, and since it is constant, it will be the same for the entire unit of wire. V is equal to IR upon L. The value of R can be written as rho L upon A. This value is substituted in this equation to get potential gradient as I rho L upon L into A. So potential gradient sigma is nothing but I rho upon A. The potentiometer is also used for comparing EMF of two individual cells. There are two methods in it. One is an individual cell method and the other is sum and difference method. Let's talk about the individual cell method. In this method, both the unknown EMFs which need to be compared are connected separately with two different keys to the galvanometer in this potentiometer arrangement. This length AB is nothing but the potentiometer wire, which is usually 2 meters to 10 meters. This is a known potential, and make a note that E should always be greater than E1 as well as E2 and as well as a sum of both. This is important so that this always remains as the driving cell. A key is provided K and a rheostat. So in order for comparison, what is done is the key K1 is closed whereas K2 is kept open, and using the standard procedure, the zero deflection point in the galvanometer is found out by tapping the jockey at various points on the potentiometer wire. The point, suppose L1, at which zero deflection is observed, this L1 corresponds to the resistance in the potentiometer wire. Hence, E1 is equal to I times sigma L1, where sigma is the potential gradient. Next, the key K1 is opened and K2 is closed. Again, finding out using jockey to find the zero null point, the point E2 is found out as I times sigma L2. The ratio of E1 and E2, I sigma L1, I sigma L2. Therefore, E1 by E2 is nothing but L1 by L2. This method is known as the individual cell method for comparison of two EMFs. Now let us look at the sum and difference method for comparing two EMFs. In this method, the arrangement of cells in this arrangement, the cells are arranged such that they can be chosen to be either in series or in parallel. The combination is such that when in series, the arms 1 and 2 are connected, whereas for parallel arrangement, arms 3 and 4 will be connected. In series connection, the connection goes as arm 1, arm 2, and then flowing through the galvanometer. So positive, negative, positive, negative. Since positive, negative, positive, negative, this is the order, the cells are said to be assisting. For parallel arrangement or for opposing arrangement, the arms 3 and 4 are connected. In this connection, the cells are so this is positive, negative, negative, positive. This is known as opposing arrangement. Now that we have seen assisting and opposing arrangements, when the key is closed and current is allowed to flow through the circuit, we use the galvanometer and the jockey combination in order to find the null point. For series arrangement, if the null point is obtained at point P, which corresponds to a length of at point P, the corresponding null point length is L1 in the cell assisting arrangement, and since these cells are assisting, the combined EMF will be E1 plus E2, which is sigma I sigma times L1. Similarly, in the opposing arrangement, if the null point is obtained at P dash, which is at a length of L2, E1 minus E2, which is, since these cells are in opposing arrangement, there would be E1 minus E2, and that would be equal to I times sigma L2. Now, looking at equations 1 and 2, we can write as E1 plus E2 upon E1 minus E2 is equal to I sigma L1 upon I sigma L2. Therefore, E1 plus using component of dividend, we can find out the value as L1 plus L2 upon L1 minus L2. This equation can be used for comparing the EMFs of both cells. The potentiometer can also be used for finding out internal resistance of the cell. In order to find it out, the arrangement is as shown here. In this portion is nothing but the cell of which internal resistance is to be found out. It is shunted with a parallel resistance and in combination with a key. So in order to find out the internal resistance, the galvanometer's null deflection is found out when current flows through the circuit. Initially, the key K1 is kept open, and the only current which flows is because of the main cell and the cell through which we need to find the internal resistance of. Supposing the point P is obtained where null deflection is seen when K1 is open. According to the law of potentiometer law, the EMF across the cell E1 will be proportional to L1 at the point P. Now the key K1 is closed, and hence the resistance R comes as a shunt over the cell E1. And let us assume that P dash is the point where the null deflection is observed. Let this be at a length of L2. So the potential across this circuit for the length L2 is proportional to length L2. Using these equations, we get E1 upon V is equal to L1 upon L2. Since E1 is nothing but the resist can be written as R plus R, where this small r is the internal resistance of the cell, and V is the potential difference across the circuit, which is equal to I into R. Substituting these values, we get it. Using this equation and substituting it over here, therefore 1 plus r upon r. Simplifying this further, we get it. This is the equation to find out the internal resistance of the cell.